We have Michael Shapiro talking about symplectic groupoid and Teichmueller space of closed genus 2 surfaces without boundary.
Thank you very much for invitation and for the possibility to give talk here. It's a big pleasure. This is a report about work in progress of Leonid Chekhov and myself. And we are kind of, nothing is written yet, but we are kind of trying to write it down. Oh, a participant is enabled. Closed caption. Okay. Yeah, thank you. So we consider one particular symplectic groupoid. It's the symplectic groupoid of upper triangular matrices. Namely, we consider the space of unipotent upper triangular n by n real matrices. This will be object of our groupoid. And what is symplectic groupoid? It's a collection of pairs, just n by n matrix B and our upper triangular matrix A, such that if you take B, A, B transpose, you will again get upper triangular unipotent matrix. So this object was studied by Alan Weinstein, like in general settings, who proves the theorem that if you have a symplectic groupoid, it kind of has natural symplectic structure. And symplectic structure for this particular groupoid, the groupoid of upper triangular matrices, was studied by Bondal about 2000, who wrote a kind of explicit expression for this symplectic structure. Now, so collection of pairs here, as we see, has a natural symplectic structure, but we can consider the projection from the pair to objects. And symplectic structure disappear, but this projection induce Poisson structure on the space of upper triangular matrices. And the log canonical coordinates on this space are just collection of coordinates xi, xj, such that Poisson bracket between xi and zj has very simple form. It's just some constant dependent on ij times the product of xi, xj. The definition, it's sort of Darboux coordinates, like some smaller change, some small change of Darboux coordinates. So what we did with Leonid, so we managed to construct such log canonical coordinates for objects of symplectic groupoid, and moreover for some small extension of pairs of matrices A and A tilde, where A tilde is this target BA-B transpose. And as an unexpected bonus, we got log canonical coordinates on the Teichmueller space of genus 2 surfaces without any punctures or holes. And such construction was not known before, at least to the best of our knowledge. So there is very famous construction when you can construct, like by Fogg and Chekhov, many people who can manage, going back to Thurston probably, who managed to construct such sort of coordinates for Teichmueller space of surfaces with boundaries with holes. But when holes are absent, so such construction was unknown. So, and this is kind of unexpected outcome of our activity on symplectic groupoid. Sorry.
Let's stop share. Share again. Yep. Sorry about that.
No problem. Okay, so let's just repeat. Basically, my talk is done, but let me just repeat in more detail. So we consider the space of this unipotent upper triangular matrices. As I said, M is this symplectic groupoid, which is a set of pairs BA, B is n by n matrix such that B, A, B transpose is again unipotent upper triangular matrix. And then it's clear we have two projections from A to the set of objects, either to kind of from pair BA, we can go to A, or we can go to the A tilde, which is BA, B transpose. So we denote this projection by S and T from, I don't know, start and target, I guess. And we also can consider sort of multiplication map on the set of pairs. So when we consider pair C, B, A, B transpose and B, A, we can compose them together in pair like C, B, A, sort of like multiplication. The set of all such compatible pairs we will denote by M2. So, and we have the following commutative diagram. So M2 is projected to M kind of to the first pair, or by P2 to the second pair. And then, so here, target of the second pair coincides with the source of the first pair. So we have this commutative diagram. So finally, claim by Weinstein is that there exists a symplectic structure omega on M such that it satisfies the following condition, that M star of omega, so we lift a symplectic structure from M to M2, and it's kind of decomposes at sum of P1 star kind of by pullback of omega, by sum of pullbacks of omega by P1 and by P2. And this condition is sort of defining. So such symplectic structure is almost unique. It was resolved by Weinstein. And then it's easy to check that both source and target map provide Poisson and anti-Poisson structure on the space of unipotent upper triangular matrices. Okay. Now, let's try to solve the following simple linear algebra question. Given a matrix B, let's try to figure out for what B we can construct such unipotent upper triangular matrix A such that B, A, B transpose is again upper triangular unipotent. So let's start with n equal 2. So then B is 2 by 2 matrix, B11, B12. Well, you able to see here, right? And I did home this computation, which is complicated, but I managed. So we will get BA-B transpose is such expression. Now the condition that, well, the result is unipotent upper triangular leads to equation that element 2, 1 of this resultant matrix is 0. So we can solve A12 from this one, and we will get the following expression for A12. And then we substitute it back into A and in A tilde. So we will get that A tilde has the following diagonal terms, which lead to condition on B that the determinant of B must be equal to 1, and also the ratio B12 over B21 should be also equal to -1. In general, we will get the following formula that for kind of if we split B, kind of think about B as in block diagonal term, kind of cut it in, this is BK is K by K block, and BK hat is N minus K by N minus K block. So then condition is that first determinant of B is equal to 1, and then this ratio should be equal to -1 power N minus 1 when N is the size of the matrix. Now remark that if we think about B as an element of GLN equipped with a standard trigonometric Hermetic structure, then this collection of BK divided by BK hat are exactly Casimir's of this Poisson bracket. So our condition boils down to the fact that all matrices which possess all matrices B such that there exists corresponding A form a symplectic leaf of this standard trigonometric Hermitics bracket, and which is given by conditions that this Casimir's are equal to -1 or 1. And let's denote this symplectic leaf by GL circle. So for GL circle, we have a map from B from GL circle, we have a map to the pair A and the tilde. Now, what we want to do now is use some sort of graphical representation of Fock nature of parameters describing triangular matrices to reformulate this condition one more time. So construction by Fock and Genscherov is the following. So we draw such a picture where yellow dots correspond to parameters sitting that describe some matrix. So each yellow dot is equivalent to some parameter. Then if we have the parameters in yellow dot and we have some kind of oriented path going like that, then the weight of the path is the product of all parameters above this path. And finally, we can define transport matrix as taking the entry I on the right side, taking the exit J on the left side, and considering all possible paths, oriented path from I to J, sum over weights of paths. Sum of weights of paths over all paths connecting I to J. So this is well-known construction. And the point is that these parameters, well, if you write our matrix in such form, then trigonometric R matrix has very simple expression in these parameters. It's really given by a quiver written here. So trigonometric R matrix in terms of these parameters look like that. That if A and B are parameters, then bracket between A and B is equal to epsilon times A times B, where epsilon is just the number of arrows going from A to B minus the number of arrows going from B to A. And arrows have of two different types. There are kind of usual arrows, and there are like dashed arrows. Dashed arrows correspond to the weight 1/2. So epsilon is equal to plus or minus 1/2 if the arrow is dashed. Now, let's go back to the problems that we described and try to describe solution of this problem in terms of this network. So we can consider such two triangles joined together, then we have network in the first triangle and in the second triangle. And this matrices network define three different transport matrices going from right side to left one, going from left one to the bottom, and from bottom, like it's drawn here, like matrices T1, T1 bar, T1 tilde, and T2, T2 bar, and T2 tilde. Then claim is the following. If S is a special anti-diagonal matrix, which looks like this plus minus ones, and Poisson bracket is like that, then for matrix B, which is obtained as T1, T2, so it's kind of, if you follow this path, it goes from the right side to the diagonal and then to the left side. And then A can be taken like, well, so to say, well, this expression, which corresponds to the following. So we have to start on the right side, go down, well, I don't know, I'm not able to show that. Well, we go from the right side to the bottom one, again, the direction of T1 tilde, then sort of glue the bottom side to the top one, but changing orientation, inverting orientation, and continue by T2 tilde and T1 inverse, which correspond to the going along this edge in the opposite direction. So as a result, we get a loop which kind of goes along this picture in the opposite way. And it's easy to compute that the result is upper triangular matrix. And then if we do B, A, B tilde, then A tilde, the result is obtained as sort of matrix obtained following the path shown here in the brown. And it's also upper triangular. So kind of schematically, it's shown here. So one path corresponds to the, well, A corresponds to the following paths that we follow yellow lines, like going from right side to the bottom, then kind of go around, changing orientations, and follow the T2 tilde, which is yellow, and following T1 inverse, which sort of has opposite direction to T1. And then second one, it's the similar thing which follows this blue color. Claims that our map from defined like that in terms of this Foggencher of parameters is Poisson, and it's not immersion. So it's well, we can see that it's some projection with fiber of dimension higher than 1, generally speaking. So okay, so kind of the restriction on matrix B can be formulated in terms of Casimirs of this bracket. Let me skip it because I not enough time. But kind of when we restrict ourselves on the right values of Casimirs, the parameters form the following quivers, like here. So this is a quiver for n equal 3. Each vertex of this quiver is equipped with one of these Foggencher of parameters, and it's this thing describes pair of matrices A and A tilde. Well, there is some theory of cluster algebras which kind of deals with that. I have no time to speak about that, but you can do some transformation of these quivers for called mutations, which behaves nicely with respect to Poisson bracket. And doing this transformation, one can transform such quiver into this one, and this one into well, this picture. And you can see that this one is exactly this thing, which is well known in theory and cluster algebras. For example, this is a quiver of so-called finite mutation type. So if you do mutations of this quiver, you'll get only finitely many quivers, which is not usual. So usually you will get, starting from one quiver, you might get infinitely many of others. But this is very special, so all such special cases were classified, and it is one of them. Well, so let's consider the case n equal 3 by 3 matrices, then and study this projection phi from our symplectic leaves in 3 by 3 matrices to the pair of A tilde. So well, this symplectic leaf, the dimension of this symplectic leaf is 6. And I want to state that dimension of the image of this map inside the direct product of well, of such space by itself is really 5-dimensional. How one can see it, it's very well known that with respect to the natural Poisson bracket on this space of unipotent upper triangular matrices, there are Casimirs of this Poisson bracket, and the Casimirs, all Casimirs are given by the coefficients of determinant A plus lambda A transpose. So you just expand it in powers of lambda, and each coefficient is Casimir. For case n equal 3, the only non-trivial Casimir is just determinant A plus A transpose, which is the following expression. And it's easy to see that this is called Markov element, and it's easy to see that Markov element of A and A tilde coincide because, well, well, it's really the proof is here. So determinant A tilde plus lambda A tilde transpose can be expressed like that, and you will see that you can factor out determinant of B. If B is an SLN, then well, determinant B is 1. So Markov elements of A tilde and A coincide. So the image is 5-dimensional, and it means that the fiber of our projection is 1-dimensional thing. But we know that our projection is Poisson map. Okay, now what it has to do with geometry. From the work of Fock and Chekhov, it's very well known that, well, we can consider the Teichmueller space of genus G surfaces with S holes. And Fock and Chekhov constructed embedding of such particular space into space of upper triangular matrices, Poisson embedding, when the number of holes is 1 or 2. It's for the case of torus with 1 hole, it goes like that. So torus with 1 hole can be equipped with so-called shear coordinates in terms of Poisson bracket. They have like very nice expressions, and each loop, well, this is fat graph drawn for the torus. Each edge of fat graph is equipped with 1 parameter x1, x2, x3. So they parameterize the kind of monodromy matrices going along this parameter, parameterize monodromy matrices around these loops. So if you take traces of these monodromy matrices, we obtain so-called geodesic functions, which has in parameters xi nice expressions. And here what's happening that when we take this surface to such 3x3 matrix, it's Poisson embedding. Now, geometric meaning of Markov element, it is just the geodesic length of the whole of our torus. And the fact that the length of 2 holes coincide means that we can glue these 2 tori with holes to each other. And the result of gluing is the surface of genus 2, but not that there exists exactly 1 parameter family of gluings. And let's recall that our fiber of our projection is exactly 1-dimensional. So natural hope is that this gluing provides us with natural coordinates of the glue. Well, this 6-dimensional space provides us with natural coordinates of glued surface. So we really parameterize the space of closed genus 2 surfaces, and it's really the case. Unfortunately, I don't have much time, but we can write explicit parameterization, and we can check that this parameterization works. Moreover, all dentist have representation in terms of cluster mutations. If we do one extra if we can add one extra vertex to that one, and the result, well, one can check geometrically that it's really true, constructing exactly monodromy matrices. And the result is the following kind of theorem, that the space of regular function on genus 2 closed surfaces can be expressed as the ring of regular functions on some skewer factored by the condition that Casimir is 1. So which allows to compute some other things, which I'm not going to tell about. Well, let me finish with yesterday I played with this chat GPT, and it wrote a poem. Yeah, which I was blown by that here. So thank you. Let me stop it.